I have two examples for you with regards to volume flow rates. So here's one example where there's basically a fluid which is being passed through two tubes, and then they join back into a tube and they continue on. Now the assumption here is that the radius actually is the same in all the tubes, and we want to be able to calculate what the volume flow rate would be, which is coming out, and we're given what the volume flow rates are in each of the tubes coming in there. So that's one of the examples, okay, so that I want to be able to talk about. And then another example, which is a pretty neat example, and I will put the reference, okay, so I originally kind of saw basically this example. I've changed this to talk about something a little bit different, but I've seen this example and I'll put the reference for that, and it was in a physics textbook from OpenStax, so you'll see that in the description below. So, you know, hats off to OpenStax for allowing people to use the textbooks for free. So please do, you can download the textbooks and then learn from them. Okay, so I'll put that for you. And this example is with regards to actually the heart, okay, and pumping. And now here I'm actually talking about an athlete, which is a little bit different than what they talked about. But I'm calculating pretty much the same thing. So we'll look at these two examples from the volume flow rate idea. Now, I do want to do a little bit of a deja vu for you, and my assumption is that you're familiar with volume flow rate. I'll put up a link up above there if you want to watch the introductory video, okay, on these concepts. Now, the main thing that you should understand is something which is super neat. And what happens is for fluids, and these are for incompressible fluids, so most of the time we'll think about them as liquids, which means we can't really compress them. So the neat thing here is that what the volume, so what we have is the volume, okay, flow rate. This is kind of how I designate it. And this is the volume flow rate coming in. So you can imagine, you know, this is the input in here, input in there. It is always equal to the kind of volume, okay, flow rate, which is kind of coming out. And this sometimes is shown with regards to, you know, the tubes actually changing. So you can think about kind of water flowing in, okay, through a particular rubber hose, okay, and then you can know that the nozzle, okay, is much, you know, thinner, the opening, and the speed, okay, of the actual fluid is, you know, super quick. So once we understand this concept that we have, you know, the volume flow rate in equals volume flow rate out, then we can use this to our advantage to calculate pretty neat examples. So here's the first one, all right? So what do we have here? We want to be able to calculate what is the volume flow rate, okay? So this is the volume flow rate over here. We have been told these two volume flow rates, okay, that are coming in here. So one is over here and the other one is over here. So that is not very difficult for us to do, actually. So within here, so we know what the two volume flow rates are. Okay, and if we know that the volume flow continues that way, so it's the same, so you'll notice that what do you have coming in, and that's 35 milliliters per minute, which means that we're going to have 35 milliliters per minute coming out, as long as there's continuity in here, and that's just the summation of the two. So that's very simple. Now, once we have this, we can actually also figure out what the speed is here. So notice that, you know, here, so this is the speed that we want to be able to calculate, and we want to be able to do it in meters per second. So now we have to kind of go back into understanding what the volume flow rate is. So volume flow rate is equal to, and what that would be is we would need the actual surface cross-sectional area of the tube that we have, and then we'd have to multiply it by the speed itself that the fluid is moving at. Now, the cross-sectional area, we have the radius of these tubes. Now, we're going to assume that this radius is exactly the same in all of the tubes, okay, within here. So the tubes do not actually change as you're going through. So if we make that assumption, okay, then we can calculate what the speed might be. So what we have is, now the 35 milliliters per minute, if we want everything in meters per second, okay, so that means we're going to have to do a little bit of unit conversions in here. So I'll do that, okay, on the side here. So 35 milliliters per minute. So that's going to test your unit conversions that you have. So this equals to, well, if you want to put it into liters, so that's 35 liters per minute. So times, now liters, you know, so how many liters do we have? And because we want it in meters cubed, well, we have 1,000 liters in 1 meter cubed. So that's the unit conversion, and you would have seen that if you watched the introductory video. And then, of course, so that takes care of the liters in here. And that's going to be multiplied by, so 1 minute. And 1 minute is obviously 60 seconds. So the minutes will cancel. And now we have our speed, which is exactly what we want. And, I'm just going to punch this all in here so that we have what the numbers are. So this is 0.035 multiplied by, well, I guess by 1 again. And then we're going to take this and divide it by, so the first by 1,000. And so that's going to give us, okay, at least in scientific notation, that answer, and then divided by 60. So I'll keep this in scientific notation. Okay, and we have this times 10 to the negative 7, and this is meters cubed per second. So it doesn't seem like it's a lot, okay, but it is meters cubed. All right, so that's the first thing that we have. Now, what I've calculated is this, right? So that's basically what I have the answer to. Now, to calculate this, the area, this one is much simpler. So if this is 1.3 millimeters that we have in here, and so this looks like, it's almost like kind of like an IV that you can think of in the tubing in the IV. Well, so this is 0.013 meters. Okay, so that's what that would be because of the prefix that we're running into. And all these tubular ideas always assume that they're basically circular, so that the area in here, okay, would have been pi, and then this is r, okay, squared. So this is going to be r, which is 0.0013 squared. So that's this. We don't know what the speed is. That's what we're looking for. And then we just found, okay, so this right here. So I'm going to duplicate it and bring it on the other side. And now I have everything in metric standard units. So I can go ahead and solve for V. Now, solving this for V is going to give me, so if I take that in here into consideration, so V is equal to, and that's going to be this right there. I'm going to duplicate that. And then I'm going to divide. Okay, so all of this is going to be divided by right there. And it's going to be divided by all of this, which is the area, cross-sectional area. So I'm going to put that in here. And let's see what that is. So I have this on the calculator already, which is great. Now divided by, I'll put everything in brackets. So pi, you can use 3.14, 159, depending on what your teachers want you to do with regards to pi. I have the pi on my calculator. Okay, so within here, so that's going to be that times 0.0013, and this is squared. Okay, and put that all in brackets, and there you have it. So what does this tell me now? So if I do this, this is going to be, so 0 point, and this is going to be 1, 1. I'll keep it to 2 significant figures because I think that's the lowest one in there. And that's going to be my speed, which is meters per second. All right. Okay, so that's what I would have in there. And that's it for this particular example. So here's the second example. This will be probably a little bit more work. We'll see about that. So we have a heart, and during exercise for an elite athlete, has been measured to pump at a rate of 35 liters per minute. So I think at rest it's about 5 to 6 liters per minute. So that's how much your heart is pumping. So it's it's a bit, and it happens every single minute. If you're exercising, this is an elite athlete. Okay, they have a much bigger capacity, and that's something that you can work towards. I'm definitely not necessarily there. All right, so we have, okay, our volume flow rate, and that is 35 liters per minute. So that's that. Now, an athlete's, okay, aorta has an approximate radius. So this is going to be the radius of the aorta. I'm going to put little a for aorta. And that's going to be 10.5 millimeters. All right, so 10.5 millimeters. Okay, so within here. And that's the radius, at least for this athlete. Blood moves at 1.5 millimeters per second at the capillaries. Okay, so that's interesting, as we can see there. So what does that mean? So we have the speed at the capillaries. So I'll put a little c in there. and that's going to be 1.5, and that's millimeters per second. So it doesn't move that fast. The only thing is we have quite a lot of capillaries. Now the radius of the capillary, notice that it is 4.1 micrometers. I'm going to keep this because I noticed that everything so far here is in millimeters in here. So I'm going to keep this back into millimeters. So 4.1 micrometers. So this is the prefix. So that's going to be 0 point. And so we're going to have to shift over 3 decimal places in here. So that's going to be that in millimeters. Notice how much smaller the capillaries are, which of course should make sense to you. So that's all in millimeters at the moment. Now, they want to know how many capillaries would be present in the athlete. So what this is actually asking about is this. So if you imagine, so if you have your aorta, right? Now, of course, it doesn't split into capillaries right away. So, I'll put ... here. But, you have a certain flow coming out from the aorta, which is 35 liters per minute. We know that the volume flow rate, if we make the assumption that that volume flow rate has to continue on. Now, of course, it's going to split, right? So it's going to eventually split, and then there's going to be all of these capillaries, right? So I'm going to put ... I mean, there's, as you will see as we do calculations, there's, billions of these things, okay? So all of them, okay, so this is all flowing through, and now it's splitting along. Now, because the volume flow rate over here has to sum up to the total, okay? Now, it's going to be the total amongst all of these. So this is a little tricky here because what happens is this. You have your volume flow rate. This is from the aorta. It's going to be equal to the volume flow rate in the capillaries. So that has to be equal. Now, the only problem is that we have many capillaries. Now, in this case, we'll assume that, so we have this one aorta in here. So from this, okay, so if we have that, and that's 35, liters per, I think it's per minute, okay, so this is what we have over here. I'll do the changing of units in just a moment. That's going to be equal to the volume flow rate. Now, if we only had one capillary, then what this would be is, all right, what's the surface area times the speed, right, that we have, or the volume over the time. Now, that's only if we had one, but we don't have one. We have many of these, and it's actually asking us in the questions, how many, right? So we have, does the number surprise you, and how many of these capillaries would be present in the athlete? So we don't have just one, so we're going to have to multiply this by n, and that n represents the number of capillaries. And if you added all of them together, of course, that should sum up to 35 liters per minute, okay, amongst all of these. So let's take a look and see, okay, how we can come across this and then figure this whole thing out. Okay, so we are after n. Now, we want to know, and I'm going to do this one by one. So the area, so the cross-sectional area, so what did they give us? So here's the radius that we have. So that's going to be pi, okay? And now this is all in millimeters that we're doing this through, all right? So I'm going to just take a look at this in just a moment. So that's pi. And now my radius, and so I'm going to change this back in. So if I change this back into meters, and so this is going to be now into meters, we would have to move it another 3 decimal places. So I'm just going to write this in. So it's going to be 4.1 times 10 to the negative 6 meters, right? So that's the radius now. And this is the change in prefix. So I'm taking this number, right? And I'm moving 3 decimal places over. And I'm just putting it in scientific notation. So you can convince yourself on the prefixes. If you've forgotten about prefixes, I'll put up a link up above there. So I have all of this. Now, I'm going to just leave it as r. Okay, so this is going to be my radius, and it's going to be radius squared right there. Now, and that would be in metric standard units. My speed, okay, in here, so notice it's 1.5 millimeters per second. So that, again, so moving this over, so 0.015 would be meters per second. And now it's all in metric standard units. And now I have to substitute all of this in here. So I have to take this, put it in for speed, and put area, put it in over here. So let me write it all out so that you can visually see that. All right, so here's the right-hand side. So I have this and I have that. So that's substituted back in here. Now I have forgotten, so I have to change this also to metric standard units. So 35 liters per minute. All right, so changing it back to metric standard units again. So there's 1,000 liters in 1 meter cubed. And there is 60 seconds, of course, in 1 minute. So the liters cancel. Okay, the minutes cancel, and I'm just left with meters cubed, okay, per second. So what would that be? So 35. So 35, and this is going to be divided by 1,000. So that's just, now it's meters cubed, and I want this, okay, still be divided by 60 because I want it per second. So as you can see there, and I'm going to put it in scientific notation. So 3 times 10, and that's what, 1, 2, 3, 4, so -4, and now everything is in metric standard units. All right, now solving for n, so I have to take my left-hand side and then divide it, okay, by all of this junk over here. So I have to take this and fully divide both sides by that, right? So this is going to end up on the other side, so that's what I would have in there. Okay, so, well, let's try it. Let's try to plug it in and solve for n. So n equals 2. So it's going to be the left-hand side now divided by, and I have to now take all that junk in there. So pi times, and this is going to be, going to put it in brackets. So 4.1 times, 10 to the exponent of -6. Okay, so that's in brackets there. Now I have to square that. And now, so after squaring it, multiplied by, and this is going to be 0.0015. That's divided by that speed. Okay, so now I have everything in brackets equals. And so as I said, it's going to get into the billions. So this is, 7, and what is this? 363,901,128. So, we're already getting, okay, millions, this is billions. And so that's how many capillaries you would have actually had. It would have to split into that many. Now, to be honest with you, so as you're going through, the speed of 1.5 is kind of exaggerated. It doesn't actually go that fast. It goes slower. And what would happen is that would blow up these number of capillaries even more. And if you look up, I would encourage you, you can look up in the reference that I mentioned, okay, or you can look it up on the net, and you'll see that we have quite a lot of capillaries. It's definitely in the billions range, and because we have those endings everywhere. And by the way, the speed can't be very quickly in those capillaries because the blood and the nutrients, they have to get absorbed, right, by all the different cells and so on that we're trying to feed. If they're moving too quickly, we wouldn't be able to feed the oxygen, we wouldn't be able to feed the nutrients and so on. So it's only at the heart in the beginning that the aorta, kind of pushes things out, and then they really slow down at the ends, okay? So that's what happens there. All right, so that's a pretty neat example. I encourage you, you can step yourself through this and then walk yourself and see if you can understand what has been exactly done in here. All right, so thanks for watching. We'll see you in a future example. Bye, everybody.